All right. Well, good afternoon, everybody. Thanks for taking your lunch hour to hear about the Yannell PHIUS Residence project, which was the recipient of the 2023 AIA Chicago Decarbonization Award, as well as the 2022 AIA Illinois Decarbonization Award. The Committee on the Environment and 2030 Commitment, Casey's happy to welcome our presenters today, April Hughes and Sachin Anand, to tell us all about the project and celebrating projects that are, contribute to the decarbonization effort, which is what our knowledge community deeply cares about. If you go to the next slide, April. Just a quick introduction. I'm Kelly Moynihan, one of the co-chairs, joined by Daniel and David, also here. Wave your hands. Hello, hello. We've been co-chairs of this KC for the last 2 years. And we're always looking for new people to join our group. You can go to the AIA Chicago website to sign up for our emails and to be tapped into all upcoming events for our KC. Go to the next slide real quick, April. Before we hit that, I'm going to recognize our sponsors. We'd like to take a moment to thank the companies and firms who support AIA Chicago at the highest level. Our 1869 Circle partners, that includes Arup, Black Spectacles, and Spectacular Design, Gensler, Goldberg, General Contracting, Ice Miller, Jan, Lamar Johnson Collaborative, Lurch Bates, Lightning Protection Institute, Norcon Inc., Patclad, Peterson, Perkins & Will, Ratio, Schuler Shook, Sierra Pacific Windows, Stantec, Taft Law, and Thornton Tomasetti. We are very thankful for their support so we can put on programs such as this. I won't read these learning objectives, but this is the stuff you're going to hear about today in the presentation. And with that, to not waste any more time, I will turn it over to April and Sachin.
Thanks, Kelly, and thanks, AIA Chicago. I do quickly, just before we make our 2 introductions, I am going to go over these learning objectives just to say that we're also going to add that because, we're going to go through and identify the ways to overcome constraints that existing buildings deal with in making the move to passive house. We're going to talk about some of those codes. We're going to talk about the specifics of variable refrigerant flow, HVAC technology and how it was utilized in this project and what some of the challenges were with that. And obviously to create this high performance demonstration project as a template for other projects in Chicago. But on top of that, also the concept that, 98% of our buildings remain year over year, and we cannot build our way through the 2% of new construction every year out of the climate crisis. So how do we deal with our existing buildings, making them more efficient and healthy so that we can meet the challenge of the climate crisis? So the title of this, Yannell PHIUS Residence, a model decarbonization. I'm April Hughes. I am president of Nurture. We're a woman-owned Chicago-based architecture firm that focuses on historic preservation and high-performance sustainable design. We have certified passive house consultants on staff that worked on this project. And we do some of the best work, I think, at the nexus of these practice areas, which is retrofitting existing buildings to meet the challenge of the climate crisis. With that, I'll turn it over to Sachin.
Thanks, April. I'm Sachin Anand with DBHMS. I'm the founding principal for the firm. The Database Plus studio within DBHMS really collaborated with April and her team on this project. And we're fortunate enough to have worked on a lot of sustainable projects in the area, in the Chicago area. And we're a team of about 100. We do both MEP design, commissioning, both enclosure and system, and do a lot of analysis and collaborate with architects to working on these sustainable projects. And it was really fun to work on this one, and happy to kind of talk to you more about this today.
So there we are. We look good. So let's talk about this project. How does a project like this come to be? Because essentially it wasn't easy, right? It was a demonstration project. And so I just like to talk a little bit about the kind of context in which this project came about. So we've been working with the client, his name's Michael Yannell, Dr. Michael Yannell, for the past 15 years on a variety of projects. This was the third in a series of projects for him. You can see at the top, the first was his net zero energy design lead homes platinum pilot residence on the north side of Chicago in the Ravenswood neighborhood. It had Chicago's first single family gray water recycling system, actually the first in the state as well. His second project was for a nonprofit Harmony House for Cats at Elston and George on the north side of Chicago, 7,500 square foot lead platinum, designed to be net zero, solar, hot water, geothermal, high performance envelope, etc. This third project was a residence that you'll see is just to the south of his current property. And his final project that we're working on right now that broke ground 2 months ago is a conservation habitat project. It's a sort of a retirement commune for a number of couples that will be living together on the shores of Lake Michigan. It intends to be a full FIUS compliant and full living building challenge, energy independent, and a 13-acre habitat restoration project. So, you know, having a client like this to work through demonstration technology to kind of show the market that these goals are achievable has been a really wonderful and interesting ride to be on with this client. So one more thing just about kind of how we got to this with him. We will also be going through the details of the pro forma. But first, I just want to take a step back and talk a little bit about what FIUS is. So FIUS is really, it's passive house, if you've ever heard of it. And maybe I'm already preaching to a choir of 30 people that know what this is. But it's a building technique that started in Germany, and it focused on super tight building envelope to minimize energy needs, right? Through like minimal HVAC. And so FIUS is really Passive House Institute US. In the United States, we have 9 different climate zones. And so we have to titrate that passive house standard to those different climate zones. FIUS also accredits builders, they accredit professionals, they administer a standard that helps to certify projects that contribute to this high performance envelope. And it really prioritizes these 5 things that you see here. So minimal space conditioning. And so today we're going to talk about that through the exploration of VRF technology, balancing heat and moisture with recovery ventilation. So that's an energy recovery ventilator, ERV. If you're going to have a tight envelope, you've got to have great indoor air quality. High performance windows and doors, a really tight envelope, right? So we have to prevent infiltration, continuous insulation with minimized or ideally no thermal breaks. Anyway, really high R values we're talking about here, and other building technologies that help to air seal the envelope. When you do the FIUS standard, there are also some certifications that sort of come that are sort of bound up within FIUS. So you also are U.S. Department of Energy net zero ready status, your EPA indoor air plus qualified, because again, a tight envelope, you have to move the air through the interior of the building, and you have to make sure that those materials inside the building aren't off-gassing and contributing to a negative indoor environmental quality, and an EPA Energy Star certification. So back to this building, where is it? It's on the north side of Chicago. If you're familiar, you know, Ravenswood and Lawrence. This is Ravenswood and Ainsley. It's really close to transit, obviously in a very hot neighborhood for schools. As you can see on the bottom left corner, that, you know, there's sort of this Victorian building stock on that corner. As you can see in the middle panel here, Michael's home that he built in 2008 is there on the top left. You can see all the solar panels and the kind of courtyard style design of that project. And this project is located just across the alley. So this is one of the reasons he got into this project, was because a developer was interested in the property, was looking to rezone it and build a structure that would have been 45 feet tall, which would essentially have infringed on his solar rights. So he worked with the neighbors, he worked with the aldermen to try to essentially fight that taller structure, and then ultimately ended up purchasing the property. And then he talked to us and he said, what am I going to do with this essentially abandoned for 10 years, derelict property, just sitting there, but sort of like still part of the neighborhood fabric, even though it was sort of falling apart. The form and the way that it contributed to the street wall were still, you know, an important part of the fabric. And so we said, well, why don't we do something hard like we always like to do? Why don't we try to do passive house and do it as a retrofit on this existing 120-year-old leaking like a sieve farmhouse? So he said, sure, how are we going to do this? Also, I don't want to own it. I want to sell it. Okay, great. So as you can see, that's what it looked like there on the right pane. So how do you create a pro forma for something sort of after the fact? And I guess I can just say this to you from the bottom, like, you know, we were already in, or Michael was already in $500,000 on just purchasing this property, right? And we had to figure out how to create a budget to incorporate as many desirable from the real estate perspective, from the buyer perspective, and from the high performance sustainability PHIUS perspective. How do we create enough budget to pay for these items? And so we kind of started at the bottom, like, what if we didn't do an addition? What if we did an addition, but it was sort of a light green touch, right? What if we did it PHIUS? And what we ultimately ended up finding out was that in order to have a significant amount of budget to be able to pay for these green technologies, in working with a realtor and producing this pro forma, we pulled a bunch of comps. We essentially found out that we could not sell this property for a profit unless we did better than the 3 bedrooms on the second floor. So ultimately what we had to do was add a bedroom on the second floor. It was the master or the primary. So that was a 500 square foot addition, 250 on each floor. First floor was a family room. Second floor was a primary bedroom. And we had to finish the basement, which means we would have to excavate it. And we did some guessing on the cost, on the pricing of this when it hit the market, because there's really no comparables in the MLS for green technology. Even back in 2017, 2018, 2019, and even today, there's really not a great way to value or search for those things, even though we sort of intrinsically feel or know that the market would respond positively. But again, a demonstration project. So this is sort of the kind of the core of how we developed pro forma. Some challenges that we had, you know, once we started really getting into this, was that when you are working on a building where you want to have a really high performance envelope, a lot of times the best way to do that and maintain the interior square footage of the home is to add insulation on the exterior of the building. But when your building is so old that zoning is overlaid on the top of it, it essentially was existing non-conforming in its own zoning. So if we put anything in the side yard, well, one, there wasn't enough side yard to even call it a real side yard, even though it abutted an alley. We would have to get special permission in order to add insulation on the outside of the home. So that was just one of sort of the policy things that we ran into, and we'll go over a few more. This is just taking a look at what that exterior condition was of the building. And there on the right, as you can see, we started to peel off the layers of cladding that had been put on building over many decades. And what we did find out, and what we had assumed appropriately, was that this building also was balloon framed, which is great because that minimizes thermal breaks at the floor change at the second floor. And that allowed us to have this continuous insulative barrier on the outside. These were the interior conditions after the demolition. And as you can see, you're seeing a lot of daylight through the sheathing here. And so on a windy day, the contractor had to add, as you can see, some bracing here, because without the cladding acting for some lateral stability, the building was definitely swaying in the breeze. And not only above grade did we sort of have daylight coming through, but we'll also talk about what was happening at the foundation. But before we do that, Satya and I are going to kind of share this slide. So we had to kind of step back and say, what are the overall solutions that we started to employ as we approached this building in order to meet Passive House Institute US standard for a retrofit? So as you can see, the orange here represents one of the strategies that we used, which is tongue and groove zip sheathing that helps to create its own weather barrier. In some cases, as you know, if you've used zip sheathing before, sometimes it even can come with insulation attached. The red dashed line, if you can see it, indicates that super important continuous air barrier that a passive house needs to maintain in order to get that air tightness. I'll go through a little bit more of sort of the exterior wall assembly and the insulative values here that you can see in the table. But one of the key products that we used was a graphite infused EPS insulation. We thought it would be enough on the exterior, but we ended up having to do a spray polyurethane foam from the inside. I'll get more into that a little bit later. If you know anything about Passive House, you'll know I've said a few things that maybe cause you concern up to this point. One is that, we're making a building larger, right? Well, some of that was driven by the demonstration and the ability to bring this to market. The second thing is using a closed cell spray foam insulation. While it has a really high R value, it has a high global warming potential because of the blowing agents. And it was sort of a last resort for the team. And maybe, Sachin, I'll turn it over to you and we can start to talk a little bit about HVAC technology and some of the other.
Yeah, so April, I think one of the things from my perspective, I think with the Passive House, the focus is really on minimizing the energy in the first big thing with Passive House, just from as the name suggests, is really having a very robust building envelope, very high R values and very airtight. One of the things which is unique to Passive House compared to some of the other rating systems is they're very somewhat prescriptive. So if you're not familiar with Passive House, if you see those bars and the numbers up at the top, which talk about heating and cooling demand and then heating and cooling load, that's one of the unique things about Passive House is so the heating and cooling demand, if people are familiar with EUI, the energy use intensity, they set targets based on where your project is located, and you have to meet those. But then it's not just about the EUIs. You also have to be they prescriptively require you, which is the load piece of it, that your building envelope should be robust enough that you don't at peak times. So in Chicago, when it's 0 degrees outside, you can't expend more than a certain amount of energy to keeping the space warm. So that starts to make it more prescriptive. It kind of raises the bar in terms of design, and in some ways it's good because it kind of eliminates this fuzzy math of the energy modeling piece, which is in that EUI demand number, and then it makes it more prescriptive. You have to design your envelope to that, period. It just makes it more robust. And we'll talk more about some of the other HVAC pieces. Like April said earlier, we ended up with a VRF system. And there may be some criticism for that in terms of it's got more refrigerant and more global warming potential. So I'll get into that in a little bit on the slides which are coming up. But it is a heat pump technology. We did use an air source heat pump technology, so it's fossil. We don't have any gas in the building. It's fossil fuel free. And you can see from some of the numbers in red on the HVAC, some of the efficiency numbers for the system we picked up fairly high. And the other thing is we get into some of the HVAC slides here, which are coming up. I'll also talk about some of the challenges with VRF. It is the emerging technology in North America. It has its challenges with cold climate like ours. So we'll kind of get into that here.
So let's go into some of the details here and start below grade. So how do you deal with an existing brick foundation? And you don't want to have to pay to underpin, excavate, etc., to deal with this from the outside. You have to figure out how to deal with it from the inside. So left to right, this starts to show like where we started and where we ended up with this detail. So at first, you know, we looked at this from the trying to maintain as much of this red line, this red dashed line that wants to go all the way around the building, having that air barrier be as continuous, hopefully, as possible. So we designed the insulation to overlap and try to mitigate that heat loss through the existing foundation. But if you move to the middle, as you can see it, and we studied it, we were trying to figure out, well, where do we put the membrane? Because ultimately, from a constructability standpoint, when we do a blower door test before we add drywall, we want to make sure that we can get to areas where there might be a damage to the membrane, or there's an area of infiltration, and we need to be able to get to that and treat that. So we ultimately decided to move the membrane so that it was on the inside face. And then when we still couldn't meet the blower door test goals, that's when we had to end up coming in with the closed cell spray foam insulation, which in and of itself also acts as an air barrier to minimize infiltration. So here is a picture of what that kind of looks like. As you can see in the middle, you see where the membrane is before the spray foam insulation, but in the middle of these two things, a blower door test or two were conducted. The pane on the left, you can see that graphite infused EPS that we added. So I'll move on to the exterior wall detail upgrade. So again, this is about the progression of kind of like the thinking where we started and where we ended up. So this building on the exterior was also clad with a rain screen. That an open rain screen was the concept at the beginning. So we were gonna, you know, add this insulation to the exterior, and we were gonna have furring strips, and we were going to have the mineral wool on the interior wall cavity. Well, as we made it through the WFI model and started to look at all of our different loads, we ended up having to add that insulation to the inside cavity. On top of which, when you have the existing non-conforming condition of getting special permission to have exterior insulation on the outside of your building, you know, 1871 happened, right? So the city's just worried about fire protecting materials. And so what we ended up having to do was sandwich that graphite infused insulation on the exterior of the building between two sheets of plywood. This was good though, because at the end of the day, it helped to reduce the thermal bridging that we would have had from all of these battens. It also was less labor intensive because the nailing pattern for the rain screen didn't have to be so prescriptive. And on top of all that, saving in labor cost, et cetera, we got that fire protection that we needed as well. And we ended up at the end of the day with actually a closed system on the outside of the house, not an open rain screen, unfortunately. A lot of decisions had to be made, not only driven by the model, but also driven by the cost model. So this is what, from the inside on the two left, the middle and the left pane, what it looked like above grade after that spray foam insulation. But what you can really see here on the right pane is this sort of layering of the materials, right? We have the air barrier, we have the graphite infused insulation, we have the plywood, but then you can see there at the bottom, we have this blue material. And so that blue material is called Henry Blueskin. It's basically like a sticker that goes over the top of all of the building materials on the outside. And it helps to add that extra layer of insurance for air infiltration into the building. And that was definitely, I would say, there were 2 or 3 products that we would definitely use again on other PHIUS residential projects of a similar constructability nature. One of them would be that graphite infused EPS. The second would be the Henry Blueskin product, and the third we'll talk about a little later. And then Sachin, maybe you can go through the differences we saw in modeling in the WFI model when we started to change some of our design assumptions.
Yeah, so you can see there's three different runs here with the WFI models. And if you look at, what we're changing here, pay attention to bullet item number 2 and then 1. That's the one with those two are kind of uh, changing and we're kind of testing things. And it's really, just as with any other modeling, what we're trying to do is optimize the design. So we need to be all green check marks and not have that red X there. So it's a matter of looking at different ways to doing this. And like April explained, there's constraints here because we have an existing structure and an existing building. So it kind of limits us to what is practical and what is possible. So it's this, what are those constraints? What are the budgetary constraints and what is the performance we need? So it's a matter of, testing, working together as a team, testing those out, working that through, and kind of analyzing it, determining what works. And sometimes it's not just the pure R value. It's also looking at, do you have space to putting that much insulation to getting that overall R value and the performance. So it's kind of like a more comprehensive overall. I'll look at it. And this WFI tool, I just want to point out for folks who are not familiar with this, is that this WFI tool is very focused on the building envelope. It does a really good job of that. It's not necessarily the ideal tool for mechanical systems, because really the core of Passive House is to getting a really solid building envelope. So it does a really good job of kind of helping you optimize that and figure that out.
Just to add before we leave this slide too, the kind of the output from the WFI model on that, the lowest bar graph on the bottom, just it was sort of for our own edification to kind of show like that where a building is matters. So this was in a shady urban context, shaded from the south side from another building. But essentially what that model shows is that the amount of insulation would have been significantly reduced. The amount of material necessary would have been reduced if we were able to capitalize on getting that passive heat gain, which we didn't, right? And that's okay. But I guess it just proves that context matters. And I think that's really important.
Yeah, and April, if I can add something else to this slide, I think one of the things, I talked about this earlier when we were looking at that previous slide about the heating and cooling demand. That's similar to the EUI. And if you notice, the numbers here are in the 5, just, typically when we talk about, buildings, we're looking in, even net zero buildings that we're saying, oh, let's be in the low 20s, and then we can get to a net zero building. Getting to a EUI close to 5, that's just almost unheard of, and that's really the power of a passive house kind of building. One of the things I can tell from personal experience is, we've done other passive house projects, and if the power goes out in the dead of winter, you're not going to lose temperature in the building for several hours. It's just the building envelope is so robust. And that's really where passive house drives, the whole efficiency argument home. I sound like a passive house salesman right now.
I'm buying. Okay. What's next here? Let's get this moving. Okay, so now we're going to talk about really nerdy variable refrigerant flow systems and some of our ventilation challenges that we had before the ventilation code changed.
Yeah. So I'll jump in here. The old Chicago ventilation code, which is at the top there, if you have a 60 square foot bathroom, you need to supply 1.5 times the airflow for exhaust for toilet exhaust. So that equates to 90 CFM. And if I do the math with the passive house standard, I only need 24 CFM. So now when I exhaust 90 CFM, to balance the building, I have to bring in 90 CFM of fresh air versus just the 24. And that's going to add a penalty. So how do you get around that? This is a code issue, and some of this has been resolved with the adoption of the new code. So that's great. But when we worked on this, it wasn't there. And this is where we had to go to a much higher efficiency energy recovery. So the exhaust is coming through the energy recovery, and we're bringing in, if I remember correctly, I think our energy recovery system, and I think it's coming up on one of the slides, is close to that 80 to 85% effectiveness, which comes at a premium. That darn little energy recovery system from Zender was like $5,000 or $6,000, you know, just the top of the line, but also top of the line from a cost perspective.
This was another situation where we had to get permission from the city in order to go with this 24 CFM situation.
So talking about the HVAC systems a little bit, you know, the choice here was to, you know, go with a VRF system. And, you know, it's starting to become more popular with residential construction and some commercial as well. And I think in a single family home, it has its nuances. I think everybody's done enough VRF over the last 5 years. And in a cold climate, it is an air source heat pump, but you know, you can get enough heat from it. And you can see the COPs there. So if you're not familiar with the term COP, coefficient of performance, what that really means for a heat pump is that so this one says, you know, it's 4.6. So for every unit of electricity that goes into that heat pump, it's going to generate 4.6 units of heat into the building. And you know, the question is always asked of me is that how does that happen? And I say, without getting into the details, that's the magic of refrigeration. The 4.6 happens at some 40 degrees outside. As the temperature outside drops, it will drop down. So it is on a curve. But even at, you know, negative 13, negative 10, negative 13, it's still pretty close to 2.5. This heat pump technology has come a long way. And if you look at some of this stuff today, it's even better. And they're continuing to improve that technology. On the next slide, we'll talk about some of the configuration, but the one thing I want to point out about VRF is that it's hard to find installers, especially at the single family home level, who've done enough of this and are familiar with this. We just worked on another single family home recently, which was completed last year, and it went through the winter last January, and we had some hiccups. We had to go back, readjust. You know, there was a little bit of hand holding. And I think if installers get more familiar with it, it's going to become these air source heat pumps will become the predominant kind of source of heating and cooling. Somebody could have said, why don't you do geothermal? You know, there's a premium that comes with it. And back then there weren't the incentives weren't there when we worked on this. Now there's newer incentives as part of the Inflation Reduction Act. So we have 2 VRF systems. I think, April, if you go to the next slide, we can talk more about that. So if you look at the left diagram, that was the original design. And if you notice the cost at the bottom was between the 2 options. So the one on the left, we had selected a more, I would call it commercial type of VRF system with a single condensing unit. That's the box you see all the way to the left, and then a whole bunch of fan coil units. And the challenge with that is, one, finding installers at the residential level who are capable of doing this, and 2, you know, the pricing for it. So we ended up going to a more residential type. So we ended up with 2 different systems, which are the ones you see on the right-hand side. One which serves the basement, and then the other which serves the first floor and the second floor. And it's kind of split up that way because the residential outdoor condensing units only go so far in size. So we ended up with 2 of them. We couldn't connect the whole house to one of them. And there's a significant cost savings. So that's kind of this push and pull. April, if we can advance the slide here, we'll show some of the plans. So we're trying to find this, you know, optimized place between how much zoning we need to do so that, you know, things are not running all the time and we can turn off things, versus how much you know, what the cost of adding more zones is. So these yellow boxes are the fan coil units. You know, very little ducting, because the more ductwork you have, the more energy you're going to expend. So in the basement, we've got this 1 unit. If we go to the first floor, which is the next slide, we have these ductless wall-mounted units. In April, if you want to chime in here, one of the things, you know, we've run into is that it's not necessarily, I've heard, is it's not necessarily something which is a aesthetic here in North America. You know, we like to hide away our things. So April, if you want to kind of talk about that and chime in.
Yeah, I would just say that we kind of had a hybrid reaction to this. One, which is to sort of normalize the idea that these cassettes can be on the wall. And in some locations, they just are, right? Especially in these larger open areas. But there are also other, and I think on the third floor, maybe we can show this. Let me flip. We did look at one point, ceiling mounted cassettes. On the second floor, we ended up obscuring these behind a louver in the wall. So you didn't see the cassette mounted to the outside of the drywall. So again, it was sort of a hybrid approach. On the second floor, it was sort of driven by space, but also it was sort of like I said, a demonstration and a way, a test. Like, can we start to normalize what this technology looks like and have it sort of be part of the vocabulary that we get used to market rate housing?
Yeah, the other thing I would add with the VRF, if you're recommending that to a client on a project, this is something we've learned over the years. And in fact, this is one of the lessons learned from this one as well, is that the maintenance regime for it is a little bit different than your standard furnaces and split systems which you have in homes. And you've got to kind of pay attention to that. And it needs the right person to doing it. It's not overly cumbersome. It just needs the right person handling it who's knowledgeable about it.
So starting to tread a little bit into the lessons learned. So yes, this project was completed a while ago, and yes, it's been a wild ride the past 5 years in construction costs. So these have not been escalated, but essentially doing this as a demonstration was to show that it could be successful and replicable. And so at the end of the day, you know, we came in between sort of like the high-end renovation schemata for a budget versus like what new builds were coming in at. And at the time, I feel like to come in under $200 a square foot was definitely a win. The other couple points of light that I think are important, not reflected on this slide, is that the project sold above asking on its first showing for a modest but real profit. And so yay for demonstration technology, and yay for showing we could do it. That was a real big win for the team. But I think the even bigger win that I feel personally for this project is that we made it a point to hire a builder that was not PHIUS certified or really knew anything about it at all. We actually hired a builder, they're called MK Construction. And they do some of their own development. They do a lot of new construction. They do renovation. And we wanted to prove to the market that, you know, this is the type of a building, this is the type of a renovation that you could see around Chicago anywhere. And it is the type of a renovation that needs to be executed with a builder that you know is going to run to Home Depot at some point, right? So how can we use as much off-the-shelf technology as possible, with some exceptions, obviously, we heard today, and building materials, but picking the right ones, making sure that we're, you know, still have that high quality, sustainability, indoor air qualification from the EPA. But ultimately, that's a huge win to be able to be part of sort of teaching the market that it can do this with individuals that maybe have never been part of a blower door test. One thing I'd like to go over is sort of that third building product that helped us achieve our final successful blower door test, which had to come in under 300 CFM. So I won't read this whole slide to you, but essentially what this shows is a catalog of how we were chasing leaks around this 120-year-old retrofit for a month. And what we had to do when we found a damaged membrane, what we had to do when we found out that a builder that had not done this before, that was using foam in some locations, accidentally used an open cell product, which is not going to help you with air infiltration. It had to be removed in some select locations and replaced with a closed cell product. But as you can see here, it was a systemic effort to close up the leaks in this home. Ultimately, the third product that I would recommend that we use is something called aero barrier. The home gets positively pressurized. It is a aerosolized technology that's granular. It is not a toxic material, but it is essentially sucked into and builds into these minute, barely visible holes, cracks, what have you, in the drywall within the interior of the home. And ultimately that brought us down from that almost 900 CFM to under 300. And the cost for this, ultimately, I think 3,300 square feet with a finished basement, including the addition, it was $2,500. I mean, worth its weight in gold. I would suggest it for any new construction build. This is just some images of the interior during these blower door tests that were all pre-drywall and where we were having some issues. One way to find issues when you're doing a blower door test can be, because the home is negatively pressurized, we're sucking air out of it, is to essentially pump smoke around the perimeter of the building and allow that to be sucked in. So there's a visual on where the leak is. The other way to do that is to use thermal imaging. And we used a combination of both of these when we were doing our blower doors in order to find some of our thermal bridging and some other issues that we had to ameliorate. So here we are, we're coming to the end and we have time for questions, which is great. So what are our recommendations? And I can go and just sort of basically say that it wasn't really the barrier of learning or information or the high level of specificity that PHIUS and a WFI model requires. For us, the thing that cost us the most in bringing a project through development to the market was time. And time was what slowed us down and had to be spent because we weren't dealing with air barriers, we were dealing with policy barriers. And so again, like by adopting a more modern mechanical code, which has happened, yay, that's great. But we still have this zoning issue in the city and we'll continue to have it. And I think that's something that should definitely be addressed. You know, still giving preferential treatment to demonstration projects in the city would be great through the permitting process. I know that's not been a high priority of the current or the previous administration, but it was at one point, and I thought it was very effective. So advocating for that. For our part, you know, this building is a more, the cladding is a more modern take. It does show that this building is different, but we maintained the street wall, we maintained the mass. We got so many comments from the community and other architects who ride the metro right past this that were like, thank God they didn't just tear this one down, right? That we sort of tried to maintain like something about the history and the character of the place and retooled an existing building for the future. And that is a demonstration that I do think is replicable and was successful. Maybe Satya, I'll turn it over to you to talk a little bit about like stretch codes and where we're at with those policies.
Yeah, I think, you know, there's policy changes which have been happening, you know, like on the East Coast, especially in New England and some of the other areas in the East Coast, passive house, you know, especially for funding. There's funding tied with affordable housing and things like that. So I think small adjustments to policy and also stretch codes, you know, in some of the jurisdictions are kind of pushing this wave of passive house and passive house certified homes, and it really is in my mind, you know, a long-term investment because with this robust building envelope, you know, that's there for at least 50 years, if not more. The mechanical systems are all going to change, and every 20 years you're going to change the mechanical systems in the buildings, and new ones are going to come in with better efficiencies, whether it's heat pumps or solar panels or water heaters or whatever. And I think it's important to kind of look at it also. With passive house, it kind of simplifies some of the design process. It doesn't leave too many options for in terms of and sometimes simplicity is key to being effective in the long run. And that's kind of what my take on this is. So.
So with that, we can take questions, and I can also just sort of wrap too in saying that, if this building were built today, there would be different codes, right? In some ways that would make it it would have made there be less policy barriers. And as we all know, elections matter. And so we, for our part, are going to continue to do the work that I know everyone listening on this call wants to do to meet the challenge of retooling existing buildings, so that we are headed toward a carbon-free future. So with that, maybe Madison, or Kelly, you can help us with some Q&A.
Yes, I can jump in here. The first question is, sorry, I missed what you did with the wall-mounted units to disguise them.
April, you want to answer them, or should I take that on? Maybe I'll start and you can join in. There is no disguising them. They're kind of built into the interior design, and I'll let the architect April here kind of chime in and
Yeah, so in all locations that we had actual cassettes, those were on the wall, right? But on the second floor, we did duct 2 wall-mounted units. Those were behind a louver, so it sort of just looked like a typical kind of wall-mounted louver HVAC system on the second floor. There was really no way. There's no way on the second floor to tell that this is a VRF cassette that's hiding sort of behind the louver.
The other thing, if I can add, which helps, which folks, it's not very apparent, is that when you do, what happens in traditional residential design or any design with HVAC is, in our cold climate, there's this tendency to drag the ductwork to the perimeter and supply it, because that's where the heat loss is happening in a cold climate. So if you go into an older home, you'll see a floor diffuser at the perimeter or a ceiling diffuser at the perimeter very often. And that's been the standard for design for many, many years. But when you build a building envelope that is this robust, you really don't need to push that warm air all the way out there. Because of that robust building envelope, you can kind of drop it in the interior wall of the room, and it still mixes well and kind of does its thing, and it's not drafty, and the conditions are more comfortable. So the other advantage of passive house is really a more even thermal comfort within the space.
Thank you for that. Another question here is, what did you do with the window flashing for the thicker wall depth and to avoid thermal bridging with metal flashing? Do you have back dams at the window sills? Are they a separate piece? Do you use a different material?
I can answer that. So with the rain screen, we did have a back dam. It was a separate unit, and if we're still on here, I might be able to find the detail of that and share it. And if not, I'm happy to share it after the call.
Great. The other question is, I notice your floor plan is pretty open. If you had more enclosed rooms, would the ductless units still be a good solution? Also, do you have any interior pics of how they look? I may have missed that. My apologies if so.
So I'll take that on. It's funny. the question asked for a picture. When me and April were doing some prep for today, we said, oh, we probably should put a picture, and then we kind of said, oh, maybe not. But anyways, in I think if we had more rooms in April, I don't know if you can go to the second floor plan. So on the second floor, and this is always, you can have more units, it costs more, but if you have fewer units, so if you see that one yellow square or rectangle to the left, that serves 3 rooms. So it's ducted, it's serving 3 rooms. So you're trying to find this optimum balance between, how much zoning you want and what it's going to cost. The more zoning you want, the greater the cost. And so you have to play with, efficiency and what you can turn down and work with that. So it's really, you could go either way. And like in a typical home like this, they would probably have a single furnace which serves the entire second floor with a single thermostat. Here we separated it out. The master suite has its own unit, and then the other 3 rooms have their own unit. So that's the zoning we did here.
All right, we only have 2 more questions here. What was the name of the blue foundation installation?
So that is actually a water and air barrier product called Henry Blueskin. Not an insulation.
Cool. And last question, what were the reasons you didn't consider radiant heating?
It's a good question. Radiant heating, so the challenge with radiant heating is really cost. And if you do radiant heating, there's 2 ways of doing it. It could be all electric. And if you do all electric, you still have to have an alternate system for cooling. Okay, or it could be hydronic, and then you've got to make hot water with either an electric boiler if you're fossil fuel free, or a water to water, or with the geothermal source, or a air to water heat pump. So when you add hydronics along with sheet metal, which you already need, you're going to add costs to the project. And one of the things which we learned from the prior projects which we did with Michael Yannell is that, when you have a very robust building envelope, you can be an all air-based system and still have the same thermal comfort. And the other advantage of an all air system is you can turn it on or off quick. A radiant has this flywheel effect, and if you turn it on, it's going to take some time to get up there with the conditions. So when you have a very robust envelope and you're trying to keep, say you're at night, you're in the bedrooms and you need to turn off the first floor, you can't just completely turn it off and then expect that at 6 in the morning within 15 minutes it's going to be up and running. So I think that's the other lesson we had learned from our past projects, and we kind of implemented that. So for cost and for efficiency reasons.
Very cool. And one more came in, and I think it might be a really interesting one, is what elements of the existing roof was renovated?
What elements of the existing what?
Existing roof.
So we kept a portion of the undamaged sheathing. We kept all the structural members, but because we were adding the load to the roof with the new PV, we did have to add additional structural members to support that load.
Great, that's all the questions. I'll kick it back over to Kelly.
All right, well, thanks, April and Sachin. This was a great presentation, and thanks everybody for attending this afternoon. Yeah, tune in for upcoming events with the AIA Chicago COAT 2030 KC, and have as good of an afternoon as you can today.
Thank you. Bye now.